GM counter. So what basically is there in a Geiger Muller tube? A Geiger Muller tube is a cylinder with an electrode in the middle. So between these two, we connect a very high voltage. Between those two, we connect a very high voltage. And there's a window here. So if any radiation is exposed to this window, what happens is the radiation comes in and it ionizes this part of the air. So if one particle is going to come in, like a beta particle, as soon as the beta particle enters, it causes an ionization. And what is ionization? Knocking off electrons. So if you have an atom, it knocks off the electron from that atom. So it creates a negatively charged electron and a positively charged ion. And what they will do is they will move to the respective terminals, electrodes. So the electrons will start running to this one, which is the positive, and the negative, positively charged ion will start moving the other way. Now when they start drifting like that, the electron is going to move that way, and the positive one is going to, negative one is going to go this way, positive one is going to go this way. As they move, they bump into other atoms, causing more ionization. And the more ionization it creates, the more number of ions begin to move. And they cause more and more ionization. It's an avalanche process. It builds up very quickly. So one ionization results in multiple ionizations on the way. So all of a sudden, the space between here and here will be filled with ions, which makes that part a conductor for a moment. And that is when we see a spark running, because once it becomes a conductor, it actually lets a current flow through, and the current is so high that it causes heating effect and lighting effect. So when you see a spark, that's because of ionization. You have seen sparks right before between two terminals. When the spark is jumping across, what exactly is happening is ionization. So it causes ionization in the space, and those ions will start moving in opposite directions, causing more and more ionizations in a rapid manner. And in a very little time, that space becomes a conductor, causing a high current, causing heat and light. So you see it as a spark. So basically what's happening is, as soon as one particle comes in, a spark takes place inside. And that spark means a current. So that will be a current in this resistor. When a current passes through a resistor, there will be potential difference across here, right? There will be potential difference across that. And that potential difference, which is set up because of that current, is registered as 1 pulse. And so this is connected to the counter. Digital counters. So this is connected to the counter. So when the counter gets an input signal of a certain voltage, it counts it as 1. And when another particle enters, it counts it as 2, and so on. So if there are 100 particles coming in per minute, this will record 100. So a GM counter includes the GM tube and the counter itself. And it's a way of determining how many disintegrations are taking place and so on. So if you put your body right next to this window, it will record some counts, because we are also radioactive. We are radioactive, and therefore it will start giving some counts. That is the radioactivity coming from our bodies. If you put some other rocks and minerals which are radioactive right next to the window, it will do the counting as well. Even if you don't put anything over there, there's something called background radiation. Background radiation means there's already radiation here, produced by us, produced by the walls, produced by the atmosphere. There is some kind of a background radiation, so it will start kind of firing now and then, registering some count. But if the background radiation is, let's say, 5 per minute, and then you bring in an object and then it increases, then you know that whatever has The increase is basically because of the object that you brought in. So you can actually figure out the actual activity. What is activity? Rate of disintegration. A, the activity is dN over dt. You can register that with the help of this counter. There are many different detectors. There's something called a spark counter. There is another one called a cloud chamber. There are different ways of detecting the presence of charges, detecting the presence of radiations, and also kind of measuring them. A GM counter actually kind of measures the radioactivity, which means the activity itself. This is something that is used in the radioactive field. Now, I said we are radioactive right now. How are we radioactive? Yes.
Is like the crackling sound from Geiger counters from the sparks? Is that just the counter itself?
Yeah, over there that is not connected to a counter, instead it's connected to a speaker. So when it's connected to a speaker instead of a counter, the crackling sounds like entry of every spark, basically. So the speaker actually kind of crackles, tuck, 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 So for every pulse, the speaker actually crackles. So if too many crackling sounds are there, it'll be like shh, it will come out like that. Well, you won't be able to count that. It's too fast. Okay, but if it is counting like, if the counts are very few, you should be able to kind of count. If it is a couple of them per minute, then you should be able to count it. Okay, so this, you must have heard about carbon dating. Carbon dating. We absorb carbon, radioactive carbon, from the atmosphere. What is the atmosphere made up of? Nitrogen, oxygen mainly, and then after that all the other little things. But where's carbon? There's no carbon there. We are talking about, we inhale carbon. And it's not the carbon in the carbon dioxide also. It's not the carbon in the carbon dioxide that is radioactive. We have radioactive carbon in the atmosphere. We call it 6C14. It is there in the atmosphere. How did this radioactive carbon come in the first place? How is it there? That's because we know that there's a lot of nitrogen in the atmosphere, right? And the atmosphere is continuously being showered by cosmic rays. You must have heard these terms, cosmic rays. What is cosmic ray? A cosmic ray is a shower of neutrons. It's a shower of neutrons. Coming from where? Coming from the stars. How are they coming from the stars? Because each and every star is undergoing nuclear fusion reactions there. Our sun is a continuous nuclear fusion reactor. Continuously, there is a nuclear fusion that's going on, continuous. And the byproducts of these things are neutrons. Even if it's fission or fusion, we'll talk about that here. The byproducts, it will spray a lot of neutrons out. And those neutrons are the ones which are sprayed out. They actually ejected very fast. They kind of get lost. They escape from those places, and then after that they are there. So neutron showers come down to the earth. Finally it comes down by gravity and all that. It comes towards the earth. And when it comes towards the earth, it hits the atmosphere. And the atmosphere contains mostly nitrogen. So when nitrogen is hit by neutron, it changes into 7N15, which is unstable. And because it's unstable, it spits out 6C14 and 1P1. So 7N15 is radioactive, and immediately it disintegrates, splits up by ejecting a proton, which is hydrogen. This is hydrogen. And the byproduct of that is C14. So if we are inhaling C14, that's because the nitrogen that was hit by neutron produced a C14, and the C14 is in the atmosphere also, in tiny proportions. But when you are inhaling air, there goes nitrogen, oxygen, carbon-14 part of it goes in. Now what's special about this carbon-14? Carbon-14 is easily absorbed by our bones. So as soon as we inhale carbon-14, it gets into our bloodstream and it goes straight into our bones. So carbon-14 enters the bones, and carbon-14 is radioactive. With a half-life of something like 5,500 years, around, not sure. So carbon-14 is radioactive. What is happening to the carbon-14? We absorb it. In fact, there are lots of absorbers on the earth. Plants, they undergo photosynthesis and all that, right? So they are absorbing carbon-14 as well. And where is the carbon-14 going? Into the trees. It's going into the tree trunks and all that. It's getting absorbed there. So the trees, the plants, they absorb carbon-14. We absorb carbon-14 through breathing. We eat plants. Animals eat plants. We eat animals. So finally, carbon-14 is kind of getting saturated in our system. Okay? So carbon-14 is kind of coming into all the systems basically through different processes, respiration, and all that. So, but then it reaches a saturation, just like salt water. You can't make it more saltier, right? You keep adding salt to water, it becomes more and more salty. But once it reaches saturation, that's it. It can't take any more. The same way, there's a saturation level that our bodies have, plants have. Once it reaches that level, then we kind of saturate on carbon-14. So right now we are kind of saturated. Are we taking carbon-14 still? Right now, are we taking carbon-14? Yes. As long as you're breathing, you're taking carbon-14. And carbon-14 is leaking out from your system too, by many processes. It is radioactive. So we are radioactive right now, and we are in that saturation point. When do we actually stop receiving carbon-14 is when we die. Okay? When we die, we stop receiving carbon-14. From then onwards, we are only decaying in the real sense. Not just in radioactive decaying, but in the real sense we decay. But the bones, they decay. The carbon-14 kind of decays. If the half-life of carbon-14 is the half-life of carbon-14 is 5,730 years, which means after 5,730 years, the activity will drop from a certain number to half of its value. So right now, if our sample is actually showing some activity, after that many years, it will drop to half of it. And then after that, it again drops to half of that. So that it goes in halves. Like for example, if I take 5 grams of radioactive, our fresh bone. If you take a fresh sample of 5 grams of it and then check its radioactivity, suppose it's giving out 1,000 radiations per minute, then what you do is check its activity after a period of time, it will drop. And it will drop according to this equation. Activity is activity naught e to the power minus lambda t. It will drop according to that equation. This is the activity, fresh activity. This is the activity after a period of time. Now, when a person dies, once they receive his dead body, they can check the activity of his bone. So they can check this and we know the activity of a fresh sample, and we know the half-life of carbon-14. Therefore, we can figure out the time when he died. You understand? With this equation, we can actually figure out the time when he actually died. But that doesn't mean the time when a crime took place. Like he may be stabbed a day earlier, and he kept bleeding slowly, and then he died one day after. We can't figure that out. The only thing we can figure with this equation is that, okay, 3 days before, that's when he died. So when they receive some dead bodies, they go for this forensic check, and what they do in the forensic checking is when was the actual time of death. Okay, that will help in the case. So this is the equation for that part, and this is what is known as carbon dating. And like this, you can carbon date even wood. When was this wood cut down from the tree? Take a sample of this, check its activity, check fresh activity, compare. You understand? So, rocks and minerals or certain things which were living once upon a time, we can actually figure out how old they are by just using carbon dating. Okay, so carbon dating is a, I don't know if you heard about a man who was found on the Alps many years ago, maybe before you were born. He was found on the Alps, on the mountain. He was buried in ice. So when they were flying above, they saw something, and then they kind of went up there, and they found that there was a person under ice. Like he was kind of transparent, maybe because of melting of ice or whatever, kind of transparent. So they started digging, and when they dug him out, they found that man to be kind of dressed in a strange manner, which is like straws as shoes. Like his shoes were made of bundle of straws tied up. So definitely it looks like someone from the very olden times. Okay, and he had some metal rod. I think it was a brass rod or something like that with him. So basically, he was preserved as it is. He was dehydrated. I mean, completely lost all his flesh and stuff like that. But his skin was there, hair was there, and things like that. So what they did was that they did carbon dating, and they found out that he was born 2,000 years before. So he was 2,000 years old, probably the time of Jesus. So he must have gone on an expedition or something. He must have collapsed and died, or he must have got into a fight with somebody and then got killed over there. I don't know. But one thing they discovered from then was he was having a metal with him, and they found that, I think it was brass. So they found brass with him, and they thought, people were actually thinking that brass was first produced, maybe 1,500 years ago or something like that. That's what the feeling was. Brass was first, the alloy was created at that time. But then when they saw that this guy was having it, and they saw it was 2,000 years old, they had to now push back those dates as well, because brass, when he's having a brass object and when the date comes out 2,000 years, that means they must have had brass at that time also. So it was more like a brass axe or something like that he was having, probably to go trekking, catching onto ice or whatever. Anyway, so that is radioactivity. We can use radioactive carbon decaying for multiple purposes, such as this. What are the other applications of radioactivity? It is used, I think I mentioned to you about tracers, right? It's used as tracers in medicine, right? It is used as tracers in medicine to detect thyroid glands malfunctions or tumors and so many other things. Radioactive substances are actually put into our system, and then they track the radioactive radioactive particles as to where they go, and by which they can figure out the problems. In industries, radioactivity is also used, like oil pipelines. They send some radioactive isotopes through the oil pipelines, and they scan different areas because pipelines are going underground, right? Now, if there's a leak somewhere, what will happen is that particular area will show more radioactivity. You understand? So if there's a pipe that's going all the way underground, when they check the activity in that area just above the pipeline, they can see the activity is a certain number, but at one spot it actually kind of bigger. That means there must be some leaking taking place. That's why it is spreading out there. So they can dig that particular place and find out what the problem is, because you can't have. And radioactive isotopes are also used in controlling the thickness of aluminum foil. When they make aluminum foil, like how thin it should be, and is the thickness properly controlled. All those things are done by radioactive isotopes, because when it passes through aluminum, if the aluminum is too thick, then it absorbs too much of it. If it is too thin, more passes through. So to control the thickness of aluminum foil, to make it one thickness, they'll do it by radioactive isotopes. It's kind of scanning. Radioactive isotopes are also used to find out defects of propellers. You know, when they make the propellers, if there's a bubble of air inside the propeller, isn't that a weak spot? So, which is not visible to the outside. You can't see that bubble from outside, because outside you see it's solid. But inside there is a pocket of air. Okay? Now, what they do is, after they manufacture this and the train wheels, you know, the wheels of trains and stuff like that, they will scan it through radioactivity. And if they find that one part of the propeller, the radiations are going pretty easily, that means there is something wrong there. You know, the absorption should be even according to the thickness. But if one spot is going through more, that means there must be some emptiness there. And like this, they can detect for cracks or defects in wheels. So imagine if the train wheel, if there is a crack or something other, if the train wheel chops into two as the train is moving, it can cause derailment. That's enough to cause derailment, because it'll break and then get in way and then take off everything else. So that's a dangerous thing. That's why they kind of scan all these things in industries to get it right. So yeah, those are industrial applications. It's used in agriculture. Radioactivity is used in agriculture. Okay. Yeah.
They use them for like satellites,
Powering satellite. Yeah. Radioactive samples are used for powering satellites as well. Even pacemakers. Yeah. Like batteries. Instead of that, you use radioactive decay. So as radioactivity goes on, that's like particles coming out. So you can use that as a current. It's got a certain half-life. That means you can just use it for a very tiny bit of a current that is required for operating those devices. Yeah. Radioactive materials are used in agriculture. Then how is it done? To make plants grow very quick, to make it produce yield very quickly. Because these days everything is materialism, right? So we just want in the least time to produce the highest yield. Even businesses are like that. So people who are actually farmers now, they want to get the vegetables, but they want to get it fast, because then they can make more profit. And that is where the radioactivity comes in. So plants absorb phosphate, radioactive phosphates, better than any other thing. In other words, plants, when they're fed with radioactive phosphates, they absorb, the absorption becomes higher. They like to absorb phosphorus, radioactive phosphorus, and it goes into their system. If it is fruits, it comes to the fruits too. Because they like that, what we do is, of course we need to put in all the good stuff, all the minerals that are required for the plant's growth. That's also required. But if you just put minerals, it's not going to take those minerals and absorb them really fast. But along with those minerals, if you add some radioactive phosphate, then what happens is in the process of absorbing radioactive phosphates, minerals also go in very quickly. And that makes the growth better. Like for example, imagine a mom wants to give vitamins, minerals to the kid. And so gives them tablets and says, okay, before your meals and all that, take this tablet. If you take this tablet, it's good for your growth, it's good for your system, and so on. And the kid doesn't like it. Kid doesn't like to take the tablets. Simple. And so what mother does then finally is, what does the kid like? Oh, the kid likes pizza. All right, let me prepare pizza now. So since the kid likes pizza, prepares pizza and then breaks this medicine, the mineral vitamin tablets, and sprays it on it, puts a lot of topping, cheese, and then presents it to the child. And because the child likes pizza, there goes all the minerals. And therefore the growth. You understand what I'm saying? So the same thing here. You take a plant, give it nice minerals to it, the urea. It doesn't absorb it that well. Yeah, it absorbs, but slowly and steadily, and makes the fruits very delicious and all that. But you don't want it. You don't want it that way. You want it fast. You want it fast. And so what you do is you add radioactive phosphates along with it. So the so-called miracle grow and all those things are basically these kind of stuff. So if you're growing vegetables using miracle grow or any other means, you can see that the growth is abnormal. You get products that are like abnormal. They are defect-free. In other words, not a single insect will eat it because they know it's bad. Insects don't touch it. Just check it and see. If you're having a vegetable garden, you won't find a single insect touching their leaves or the vegetables. You will get those vegetables like as it is, and they're big, but they're tasteless. Yeah, that is the problem these days, like materialism. Farmers need business. They want to make lots of products in the shortest time. I've seen some mango trees that are this tall. Now I've seen both kind of mango trees. If you go to India, all the big mango trees, few mangoes here and there, and they're very tasty and delicious. They're natural and they take time to grow. When I've seen in the Middle East, Abu Dhabi, there was a palace, and around the palace I saw mango trees, this tall mango trees. It had more mangoes than the number of leaves. It had more mangoes than the number of leaves. Abnormal. And the mangoes are so beautiful to look at. I'm pretty sure those are growing it are just growing it for the fun's sake, just for show. They won't eat it. And nobody touches it. I mean, the insects don't touch it also. Yeah, so insects know better than us, okay, in that manner. Insects know which food is good, which is bad. If you leave some food outside, you will not see ants coming and taking it if they know that it's bad. On the other hand, you leave something that's very natural, which can decay very quickly. Insects, ants, and all those will start tackling it. They like to take it. Okay. Anyway, so that is something about radioactive applications. It's applied in industries, in agriculture, in so many places. Coming to linear accelerator. Now, linear accelerator is a device. Linear accelerator is a device that accelerates particles to high speeds so that we can make it collide with another nucleus and transform that nucleus into a radioactive isotope. So basically, to produce artificial radioisotopes, we need to bombard some nuclei with particles. And in order to bombard them, you need these particles to get to high speeds. And how do you make it go up to high speeds? we use these things called accelerators, and one of them is called the linear accelerator. Now, the linear accelerator normally goes 3 miles long. The accelerator itself is like 3 miles long. And how is it constructed? It's constructed out of tubes. Like the first tube is that small. The next tube is longer. The next tube is still longer. The next tube is still longer. It's progressively longer and longer. It goes on. I cannot draw all the 3 miles long. So the tubes go on like this, progressively increasing in length. And alternate tubes are connected together electrically. Alternate tubes are connected electrically. To a high voltage. Very high voltage. So when you connect this like this, around that point, you actually introduce the particle that you want to accelerate, be it protons. Let's say protons, bring the protons and just create them there or insert it there. What's a proton? Just a ionized hydrogen atom, right? Ionized hydrogen atom is a proton. So bring it there. As soon as you bring it there, if this one is a positive potential at that moment, oh, wait a minute. This is not DC. I was thinking of something else. That's AC, high voltage. It's alternating current. So at a certain moment, this is alternating. You may have a positive potential here and a negative potential here. You may have this one is positive and this one is negative for a moment. And then it switches cycles to make it negative and positive. So if this cylinder is negative at a certain moment, what will happen to this particle? It will be pulled in or accelerated. And once it gets pulled into it, once it's inside the cylinder, it is in an equipotential zone. And once it's inside the cylinder, it is in an equipotential zone, which means it won't accelerate anymore, but it will keep drifting because it's already got a certain speed. And now when it comes to the opening here, the cycle changes and makes it positive, negative. So when this becomes positive, negative, again there is acceleration from here to here, which means it's going to go faster. And because it's going to go faster, it's going to drift for a longer distance in the same period of time, which is half a cycle, right? Half the time period. For half the time period, it's going to travel. So basically, half the time period it is supposed to spend inside the tube. And now after it spends the time inside the tube, immediately the cycle changes. There is an acceleration here, and then it drifts with a constant velocity again. So every time it comes to the opening, it will get accelerated, and then it drifts with a higher velocity. So the velocity keeps increasing as you go from tube to tube. That's why you need longer and longer tubes, because it is supposed to spend the same amount of time. You want it to spend the same amount of time inside the tube, so the tube has to be longer and longer. And after a distance of 3 miles, the particle is going to come out with a high speed, almost 1/100th the speed of light.
The largest one along is 16.6 miles.
The linear accelerator?
Yes, the one that is, well,
Yeah, I don't know. I thought it was like 3 miles or something. That was the first one. 16 miles?
Yeah, the particle accelerator they have at CERN.
Are you talking about linear accelerator or cyclotron?
I don't know. I just looked up side of the particle accelerator. It's 16.6 miles.
Yeah, but what's the name of the accelerator? This cyclotron is also an accelerator. Yeah.
Is the cyclotron merged just in a circle?
Circle. Yeah.
That's Cyclotron.
So that's cyclotron?
Yeah, sorry.
The total length is what they're talking about, like this, yeah. 16 miles is like, for a linear accelerator is like too far. Yeah, but this is the exact process by which it goes, and finally when it comes out from the last tube, it is ready for collision. So now you can actually make it bombard into another nucleus, and that will cause radioactive isotope. So it will cause a radioactive isotope right there. So to create radioactive isotopes, linear accelerator is something that can be used. Of course, linear accelerator is not very convenient way of doing it, and that is why we have what is known as a cyclotron. So what is a cyclotron? A cyclotron is it's actually a hollow cylinder which is split into two, somewhat like this. Like two Ds. These are two cylinders. Okay, so if you can understand this, it's like one cylinder. It's like one cylinder cut into two and separated. It's one cylinder that is cut into two and split. That's how it will look like. And these two cylinders, Ds, I'll call it Ds. The two Ds are connected to an alternating voltage, a high frequency alternating voltage. Now, drawing the same thing from above, it's like this. That is the same view from above. Of course, it's not a good drawing. Okay. So this is called a cyclotron, and the voltage that is supplied between these two is high voltage of a certain frequency. Now the particles to be accelerated are brought into the center. So when, let's say, you brought a proton to the center and released it, at that time if this potential on this side was negative and this side was positive, then it will accelerate and enter that spot. Now you don't want this charged particle to keep drifting straight. You want to turn. And to turn a charged particle, we use what method? Magnetic fields. Now, if I'm going to consider this to be a positive charge, and I want to make this positive charge turn, I need to apply a magnetic field. So let's say I put a magnetic field into the board, like top to down, like this. If I put a magnetic field from above, so magnetic field is in. Now you can use your left hand rule. Magnetic field is in. Since it's a positive charge, current is the same way. So which way is it going to experience a force? Upward. So therefore, it will take a turn that way. And what is the radius of the turn that is going to take? You know this equation. The radius of the turn it's going to take is mv over bq. Right? Why is that equation there? Because the centripetal force is equal to the magnetic force. Remember that? The centripetal force, magnetic force is BQV, is equal to centripetal force mv square over r. one of the v's knocks off, and then you get that equation. So it takes a turn of radius r1 depending on the speed v1. It takes a radius of turn r1 with the speed v1. And so mass is not changed, magnetic field is same, charge is the same, so the radius that it's going to take depends on the speed. So what happens when it enters that space? The cycle changes, and then it accelerates from here to here. Now it's going faster. Now the speed is v2, so this is v1. Now it's going with the speed v2, and therefore it will take a bigger radius. So it's going v2, and the radius it takes is r2. So r2 is going to be mv2 over bq. And like this, next time it's going faster, so it makes a bigger turn. And then it takes a bigger turn, and then it takes a bigger turn, and it takes a bigger turn, and bigger turn, bigger turn. So it keeps doing this, traveling miles, and when it is really fast, they kind of open up a window, and using an electric method, they deflect it out of the place. And now it's ready for collisions. The cyclotron can be as big as this room. You can actually have it spinning round and round inside the space. All right. So what is V1? BQR1 over, correct? That's B1. No, that's V1. V1 is BQR1 over M. If it is moving here with the speed V1, how long does it take to go up to here? How long? How long does it take to go from here to here? What's the distance traveled? Huh? What's the distance traveled when it goes from here to here? The radius is R1. What's the distance traveled? Half a circle. Pi r. Okay? So if it is traveling with this speed, how long will it take to travel that distance pi r1? How long will it take? What do you do? Distance over speed. The distance is this. Speed is this. Over m. R1 cancels with R1. So what is it coming out to be? Pi m over. That is time t1, which is the time spent from here to here. Now let's look at time t2. What about time t2? Time t2 is going to be the distance pi r2 from here to here. Pi r2, but with a higher speed, v2, divided by v2, which is bq r2 over m. Now what do you see here? They are the same. It takes the same time for it to go from here to here that it takes from here to here, that it takes from here to here, from here to here. It's the same time. And what is the time supposed to be? What is this? What is T2 in relation to this? Is T1, T2, now you saw that T2 is this, T1 is also same thing, pi m over bq. What is that T1 or T2? It's the time taken for it to spend from here to here, right? Is that the time period? What's time period? Time period is time taken for it to go one full time. So what is this? T1 and T2, what is that? Half a time period. So what is time period then? If this is T2 or T1, then what is time period? It will be twice of that. Time period is 2 pi m over bq. This is a time period. If that's a time period, what's the frequency? It'll be inverse of this. So it'll be pq over 2 pi m. So after building a cyclotron, depending on what charge you're trying to accelerate, and depending on what mass you are accelerating, you can decide what magnetic field you want, and then you can decide what frequency you want to put in. You get it? So you can choose any magnetic field, you can choose any particle that you want to accelerate, and you can calculate what frequency need to be put here in order to successfully accelerate it and bring it out. Now there is a little problem with this gadget. The problem is this: when it starts going faster and faster, watch this. When it's going faster and faster, see the time t1 or t2. Look at this. Time depends on magnetic field, charge, pi, and mass. When this charged particle starts going faster and faster, we normally talk about this mass as the rest mass, which is a mass when it is not moving. But when it starts approaching the speed of light, it becomes slightly heavier. As it starts approaching the speed of light, mass starts getting bigger. That's through the theory of relativity. Okay, the mass dilation, changes in the mass. This is the rest mass. When something is moving, what's the rest mass of an electron? 9.11 10 power negative 31 kilograms. That's rest mass. But the electron, if it is moving at a high speed, its mass is not that. It's slightly heavier. So what happens when it starts speeding up towards the end? The mass starts increasing. That means it will spend more time inside the D. So if it spends more time in the D, then your frequency goes offset. Because if it's spending more time in the D, it will be coming up to here. Meanwhile, the cycle has changed. Then what will happen is it will get decelerated. If the cycle is changing at a different place than at the mouth, at the edge of this, then it is going to get decelerated. And because of that, a cyclotron suffered from that problem. That is, the particles were not able to reach high speeds because the mass was changing. And that's why they changed it. They changed the structure of this one to what is known as a synchrotron. Cyclotron became a synchrotron. A synchrotron is a slight modification to the cyclotron to make that effect lesser. So the mass is getting bigger. When is the mass getting bigger? More towards the edges, right? It's more towards the edges. So you can increase the magnetic field then. You can increase the magnetic field in proportion to it. Then your timing will be perfect. You get it? So in a real synchrotron, the magnetic field is not uniform everywhere. Over here it is not as strong. Towards the edges it gets stronger and stronger and stronger. And that way they were able to get it in sync. And therefore get higher speeds. Make sense? That's called a synchrotron, just for your information's sake. But this is an important thing. You may use it. I think the recent ACT also did. No, not this. Yeah, it has come. I mean, they just throw this thing and then they talk about this and give you some graphs and stuff like that. So, yeah, this is called a cyclotron, and the frequency equation is that one. You don't have to memorize those equations. You can just bring it out by just discussing about what's happening. Coming to nuclear fission and fusion, the last parts. Nuclear fission is the breaking up of a heavy nucleus into lighter nuclei. Nuclear fission is the splitting up of a is a splitting up of a heavy nucleus into lighter nuclei with a release of energy. Splitting up of a heavy nucleus into a lighter nuclei with the release of energy. Now, how is the energy coming out can be explained more using the binding energy per nucleon versus a nucleon number. You know the graph that I drew? That graph? You can explain that by using this. So let's say, for example, you take uranium-235, uranium-235, 92 uranium-235, which is right there. And if you break it into two, if you break that into two, by the way, uranium-235 is more fissionable than uranium-238. That's one other issue that we have in fission. In natural uranium, we have hundreds of uranium-238 for one uranium-235. So when you say that, okay, we have uranium fuel and we can just create fission on it, you can't create fission on uranium-238 that well. 235 is more fissionable. So what happens is when you break that down, I'll give you the numbers. When you break uranium-235, uranium-92, uranium-235, how do you break it? Is by making a neutron come and hit it. A neutron comes and hits uranium-235, splitting it up into two. It just splits it up into two. Basically what happens is, this is a slow neutron. A slow neutron. A slow neutron can cause oscillations in the uranium itself. A slow neutron causes oscillations in the uranium, and because of the oscillations, it actually kind of splits up into two. Okay, like it changes into a dumbbell shape, and then after that it snaps into two. Now when it snaps into two, the two need not be exactly equal proportions, equal. So this one, when you split it with uranium neutron, a fast neutron just passes through without causing much damage. It's like this. If I send a fast stone, very fast stone through that glass, what will happen is that fast stone will just go through that and create just a tiny hole wherever it just passed through. It won't shatter the glass. But then if I take a stone and throw it gently or slowly at the glass, it sets up a vibration on the glass that snaps the whole glass into two. You understand what I'm saying? Just like that, a fast neutron won't cause breakup. Slow neutron does. That is why when you want to break a uranium into two pieces, you need to first slow down the neutron and then send it for fission. Otherwise, it won't do it. So these are slow neutrons. When slow neutrons go and hit here, the products that are formed are sometimes lanthanum and bromine, sometimes barium and krypton. Products come out in different manners. Common products are lanthanum and bromine, or barium and krypton. But they'll be like roughly of close masses. I'm just giving you an example. 56 barium 141, 56 barium 141. It's a radioactive substance. Plus krypton 36Kr92. 36Kr92 plus there's an issue 256. Yeah. Now, what is the total number at the bottom? 92, and this is 92. What is the total number at the top? 236. Add this up, how much you get? So the number of neutrons is now less by 3. So therefore, 3 neutrons are spit out. 3 neutrons will come out as a result of this reaction. And of course, we have energy coming out. Huge amounts of energy.
Is that how nuclear bombs work then?
Yeah. Atom bombs. Yeah. Now, this is a big amount of energy. Where is the energy coming from? Watch this. Where is 235? 235 is here, at this level. When it breaks up into 2 particles, where is barium and krypton on this graph? Where could it be? Higher, somewhere here. Now look at this level and look at this level. It was, okay.
We were struggling.
See this one over here? This one is less stable. After breakup, it becomes more stable. That means this much energy is given out. And that is the energy of fission. Make sense? This one is less stable. This one is more stable. So when anything becomes more stable, it has to give energy out, right? Like look at this marker. Is this stable over here? No. Now it has reached more stability. So it has to give up energy. So when something becomes more stable, it has to give up energy. And that is exactly what happens here. This uranium is unstable in terms of the stability graph, this one. Binding energy per nucleon is less here, but after breakup, they have more binding energy per nucleon, which means it has to give up energy. Yeah.
If energy is produced by fission and consumed by fusion, how is...
Say it again?
Is energy not consumed by fusion? Like fusion?
Oh, we're getting there, we're getting there.
So like, how does this work?
We're getting there. So, do you understand this part of it? Why energy comes out in fission?
I get...
You got this part of it? Now, these are fast neutrons. Those 3 neutrons that are produced there, not always 3, sometimes 2, they are fast neutrons. They cannot do any more fission. They cannot do any more fission. Now, if these fast neutrons go and hit other uranium-235 nuclei, nothing is going to happen. So what you need to do for an atom bomb, you have to slow these down. To slow these down, we use a material called a moderator. Heavy water is a moderator. Graphite is a moderator. So a moderator's job is to take these fast neutrons and slow them down and then let them go into the fuel again. And so when these fast neutrons go and hit the uranium, it is not going to do anything. Therefore, we need moderators to slow down the neutrons and then go and hit the other uranium. So if this goes on, this is what happens. Uranium-92, uranium-235, when it is hit by a neutron, produces barium, krypton, but then it produces 3 neutrons. Now each of these 3 neutrons can be slowed down by using a moderator and then sent further. Now these will go and hit another uranium and produce 3 more neutrons. And this will hit another uranium and produce 3 more neutrons. And this will hit another uranium and produce 3 more neutrons. And these 3 will go and hit other uraniums and produce 3 more. You can see how it grows. Starts with a single neutron, becomes 3 neutrons, next time it is becoming 9 neutrons, next time it becomes 27 neutrons, then becomes 81 neutrons, then 243 neutrons. It keeps building up. And this sudden build-up releases a huge amount of energy, and that is the energy that comes out in nuclear fission.